So, good morning, everyone. Welcome to lecture 12. So, in the last class, we derived the linearization, for example, of the stretch and also for the change in angle, I guess, right? And then I left it to you that you can derive the linearization for the change in volume, for the surface area ratio, and all other things. Okay, the procedure is the same. You just have to keep the most significant term in u, the displacement. Okay, and you should really do that exercise because that will help you see how linearization is done, and of course at least one of the questions in minor will be from the linearization. Okay, all right, so today we are going to discuss another very interesting topic, which is also called polar decomposition of deformation gradient. Okay, so we all know what deformation gradient physically does, right? So it's locally you have these infinitesimal line elements and they get mapped through the deformation gradient. Okay, so we say that dy is equal to big F dx, and this local map is invertible. So for every d small x, there is a unique d small y. Okay, so there is a one-to-one correspondence between the material line elements in the two configuration. All right, which means that this big F has to be invertible. So due to this one-to-one correspondence, big F turns out to be invertible. Okay, so that's the property of a function. No, if there is a one-to-one map, then the inverse also exists. So big F has to be invertible, and you know that big F has a matrix form, right? When you express it in a coordinate system, it's a second-order tensor, but when you express it in a coordinate system, it has a matrix form. And since it has to be invertible, the invertibility condition for a matrix, all of you know that all the eigenvalues must be non-zero, or in terms of determinant, the determinant must be non-zero. Okay, so this tells us that det f has to be not equal to 0. All right, in fact this can also be used to show that det f is actually greater than 0. For all continuum mechanics deformation, det f is not just not equal to 0, it is also greater than 0. Can someone tell me why that should be the case, that det f should be greater than 0? For example, you can recall that when we worked out the volumetric change, we saw that dv, if I say let's say dvy, that's equal to det f into dvx, isn't it? So dvx is the undeformed volume and dvy is the deformed volume. So x and y denoting the two configurations. All right. Now, suppose that det f is less than 0, then what will happen? If it is less than 0, then the local volume in the reference configuration is just vanishing in the deformed configuration. But that is not possible for any continuum mechanics deformation. Whenever a volume is deforming, the local volumes will change to something. It cannot vanish. It will remain positive, right? The deformed volume should also be positive. It can't be negative. Therefore, the delta must be greater than 0. Okay, so that's the restriction on deformation gradient in continuum mechanics. But this gives you a very nice decomposition of deformation gradient, and that is on the basis of what is called polar decomposition. So you can write then any deformation or any second order tensor with positive determinant as a product of rotation tensor big R, R for rotation, times of symmetric positive definite tensor U. So this turns out to be rotation tensor whereas U turns out to be symmetric positive definite. So that's on the basis of polar decomposition. Okay, so there is a proof of force and it is there on Wikipedia. You can go and have a look at it. Okay, so symmetric positive definite, what does that mean? Of course, symmetric means U is symmetric, that is U equal to U transpose. And positive definite means all the eigenvalues of U are positive. Okay, so this positive definite means all the eigenvalues of U are positive. And there is in fact a mathematical statement also for positive definite that U times X dot with X. Okay, so this is also called quadratic product. U times X dot with X has to be greater than 0 for all X not equal to 0. So if you take any arbitrary non-zero vector X and work out this quadratic product U times X dot X, then this turns out to be greater than 0. Okay, this quadratic product you can also write in component form as Uij xj xi. Okay, simply you see, first of all you have to do ux, which is matrix times vector, which is this thing uij xj, and once the ux, which is itself a vector now, has to be dotted with vector x again. Okay, so that's the property for positive definiteness. And polar decomposition simply says that deformation gradient you can break it into product of big R and big U. All right. In fact, there is another decomposition which is a tensor V into big R. So you can work out either of the two. I mean, you can express F in either of the two form. And V also turns out to be symmetric positive definite. All right. Now, what is the nice thing about such a decomposition? It is really very interesting decomposition. Let us see what's so nice about such a decomposition. See, U being symmetric, first of all, U is symmetric, right? Being symmetric means all its eigenvalues must be real, right? You must have learned this in your math class, or if you have not learned, you will certainly learn it down the line. Have you learned this yet? All its eigenvalues must be real for a symmetric matrix. Furthermore, the corresponding eigenvectors are perpendicular to each other. So supposing that the eigenvalues are lambda 1, lambda 2, lambda 3, then the corresponding eigenvectors we denote it by the vector small r I, sorry r1, let us say. Then for lambda 2 it is r2, and for lambda 3 it is r3. Okay, and because of the orthogonality, the r1 dot r2, for example, is 0. In fact, you can write it in index form also, ri dot rj, that's equal to delta ij. Okay, that's a property of these eigenvectors. So eigenvectors corresponding to different eigenvalues are perpendicular to each other. All right, so that's a very nice property of U. And this also allows you to write down what is called eigen decomposition of U. So this also means that you can write U as lambda I Ri tensor product Ri. Now is this expression okay as per the summation convention? Anyone? No, that is true, because there are three. I is appearing thrice and no index can appear more than twice. If it's a free index, it has to appear only once. If it's a dummy index, it can appear only twice. But here we have I appearing thrice. So this can't be written in summation convention form. So you have to explicitly mention here that I goes from 1 to 3. Okay? Because we really want I to appear thrice here. But since it is not allowed as per summation convention, so we will explicitly mention this summation, that I is going from 1 to 3 and there is this I. So this is also called eigen decomposition of U. All right. And in fact, if you think of the matrix form, then this U matrix, so which I denote by this brackets. Okay. So this you can write as the matrix by the eigenvectors of U, which are R1, R2, R3, times a diagonal matrix having eigenvalues on the diagonal, times the matrix of eigenvectors but transposed. So that's also called eigen decomposition. And I guess you must have learned this also already. Eigen decomposition slash diagonalization of U. All right. Let us also notice a very interesting property about U. So we wrote that F is equal to RU, right? And you remember this formula for stretch that was So if I write lambda square, lambda denoting stretch at a point x, and for line elements having direction n naught, so that was f transpose f n naught dotted with n naught, isn't it? And similarly for the angle change, if you recall, cos theta, if I say theta y, for y denoting the angle in the deformed configuration, so cos theta y, that was f transpose f n naught dot with m naught divided by lambda of n naught times lambda of m naught, isn't it? The lambda along n naughts and m naught. So what you see is that you have f transpose f appearing in these formula. Let's work out what is f transpose f based on the polar decomposition. So f is Ru, so f transpose f is then simply, so I'll just write here, f is Ru transpose into Ru, which is U transpose into R transpose into R into U. Okay, and R transpose R will be identity because R is a rotation tensor. Remember, for rotation tensors are orthogonal tensors, and they have the property that inverse of R is same as R transpose. Therefore, R transpose R, this thing is identity, which means this is equal to U transpose U, or U square because U is symmetric. This is such a nice thing, which also means U is simply square root of F transpose F. So what you see is that in these formulas here, so in this formula, for example, what is appearing here is U square. Similarly here, it's U square. Okay, and likewise, if I simply write here for dvx and dvy, you have dvy is equal to det f, which is det of ru into dvx, but determinant of r into u is same as determinant of r into determinant of u, right? So this is same as det r into det u into dvx. That's a property of determinant. But r being an rotation tensor, the determinant of r is simply 1, right? Which is finally det u into dvx. So even here you see that only u is appearing. So rotation part is not appearing. It is just u which is appearing in these formulas for change in length of line elements, change in angle between line elements, and change in the volume, local volume. It's just the u part that is appearing. Okay, so what's the recipe to obtain u? So to obtain u, you simply, first of all, you will have big F, and then u you can obtain using this formula. Work out F transpose F and take the square root. And once you have gotten u, then big R is simply from the polar decomposition. So big F is equal to R times U. So big R is therefore big F into U inverse. Okay. So you might be wondering, how do I get, first of all, so let me again write here. So what I said is that to get the decomposition, to obtain polar decomposition, you have to do the following. Number one, obtain F transpose F. Okay, because F will be known to you, obtain F transpose F. Number two, then you say that U is equal to square root of F transpose F. And number three, finally, this big R is equal to big F into U inverse. Now here you have two very interesting um, expressions. One is square root of a matrix. See, a second order tensor. How do I take the square root? And then how do you take the inverse? Can you have an explicit formula for the inverse or for the square root? Now it turns out it is easier here because your U is symmetric and positive definite. That's why it is easier. Let me show you why. So I said that this U being symmetric positive definite has this eigen decomposition, right? Which is, you can write it as summation over I lambda I Ri tensor product Ri. Okay. So let us see what is U square then. So U square will simply be U into U. So you have one summation over I of lambda I Ri tensor product Ri times the same U. And then here I won't use summation over I have to use some other index, let us say J, lambda J, Rj, tensor product Rj. And then how do I work out this multiplication of two second order tensors? So you have already seen from my previous class, the inner ones are to be dotted. The inner ones, they have to be dotted. Dot them. So what you have is, of course, you have double summation now, summation over I and j. And see, lambda I and lambda j, they are scalars, so you bring them all here. And then you have to dot ri and rj. That also becomes a scalar, no? After being dotted. So that's ri dot with rj. And then what remains, you write it. That is ri tensor product rj. So this is what remains. Okay, so that's the square. But let's work it out carefully now. You see this Ri dot Rj, I said that because they are eigenvectors, they are perpendicular to each other. So it is simply delta Ij, isn't it? So this is double summation over I and j, lambda I, lambda j, delta Ij into Ri tensor product Rj. But very interesting, what does delta Ij do? It is going to annihilate one of the indices, right? Because delta ij is 1 only when I is equal to j, otherwise it is 0. So it is going to get rid of one of the indices. Let us say j goes away, and wherever you have j, that has to be replaced with I. So summation over j will be gone, and wherever you have j, you replace that with I. So that means you just have summation over I, lambda I, lambda j, this j becomes again I, and this Ri tensor product Rj again becomes I. Okay, so you have 4 times I appearing here, and again that's why you need this summation symbol explicit. And this, of course, you can also write as summation over I lambda I square little ri tensor product little ri. So do you see that u and u square have very similar decomposition? Because it's symmetric, therefore whatever is the eigenvector of u, of course u square also has the same eigenvector. That's why it has the same type of decomposition. And the eigenvalues are simply, one has got lambda I, then the u square has got lambda I square. Okay, that's very nice thing about symmetric matrices. And likewise, so what you see here, how to get this square root then? So F transpose F, so this is actually U square, so this is F transpose F. So you first of all work out F transpose F and do its eigen decomposition. Okay. And then U, so from here, U is simply summation over I square root of lambda I square Ri tensor product Ri. Okay, so the eigenvalue of F transpose F simply have to be square root. You have to just take its square root to get the eigenvalue of U. So that was quite easy. Taking the square root, therefore, here is easier. And how to take the inverse? It turns out inverse is also easier. U inverse. So once you have the eigenvector of F transpose F, the eigenvector of U is also the same, and U inverse also has the same eigenvector. And it turns out U inverse has this decomposition, summation over I. The eigenvalues are simply inversed. 1 over lambda I, Ri, tensor product Ri. Okay, so this is how you can get um, decomposition of U, U inverse, or U square, all of them. All right. So this was just some math how to get U and R. And what you see is that U, it is U which is appearing in these formulas for stretch or for the angle or for the volume change. It's U which is appearing. So certainly it has some nice physical meaning also. So let us try to explore the physical meaning of R and U. Physical meaning of R and U. So Rahman is saying a square root will be there in U inverse. No, there won't be square root in U inverse. See, I have just written 1 by lambda I. It is not 1 by square root of lambda I square. It is just lambda I. Because U has got just lambda I, no? So U inverse will have 1 by lambda I. And U square will have lambda I square. Okay, so let's see what's the physical meaning. So we saw that this big F is decomposed as R into U. And then we know the transformation that dy is equal to big F into dx. So this then becomes dy equal to big R, big U into dx. But you see that this means you can also write it as big R into U dx. Okay. And likewise, if you think of the other decomposition, it is V into R into dx, which is same as V into big R into dx. By the way, once you have R and U, how do you get V? So what's the relationship between U and V once you have gotten R and U? So I'll get to that. Let me just finish whatever I had started. So let us try to understand what is this actually implying. So somebody is saying if lambda I will be negative. So lambda I cannot be negative. You see, because lambda i's are the eigenvalues, right, of U, and U is symmetric, positive, definite, and by that property, the eigenvalues have to be positive. Okay, so each of the lambda i's are positive. So that's a very good question. So because each of the lambda i's are positive, you can simply take the square root. Okay, so let us see what is its meaning. So what this says, no, that you have this reference configuration from which you just apply U part and then you get something, and furthermore you apply then the rotation part. So what it says is that locally you have these line elements. So U part is going to bring in change in length of the line element, change in angle between line elements, change in volume. So all that is done due to U. But R part being rotation, it is simply rotating the this neighborhood. So it is simply rotating it. So all the deformations are actually occurring due to U only, and R is just doing the job of rotation. So I can say that all the deformations are occurring due to U only. And R simply rotates rigidly, simply rotates the local deformed elements. Okay, so you can, for example, say here that this is like dy prime, which is equal to U into dx. And here finally you are getting dy, which is equal to big R into dy prime. But although this R is simply rotating the local deformed elements, but it is not the global rotation of the entire body. It is just a local rotation. So what do I mean by that is that you see this big F is a function of x, no? So when you work out the decomposition, this big R turns out to be a function of x, and u also turns out to be a function of x. So R and u, they are both changing in the body. So therefore this R is also called local rotation. It is just a local rotation. It is changing from one point to the other in the body. So it does not correspond to one single rotation for the whole body. So it is, therefore it is not like a rigid rotation of the body. If it were a rigid rotation, then it must have been the same for every point. So I'll make this qualifier in red, that R is not the global rigid rotation of the body, because it is changing with x. Okay, it is at best, it is at best the local rotation. You see, you have two terminology: local rotation and global rotation. Global rotation means it's the same at every point in the body, but local rotation is something which is changing from point to point. Okay, so local rotation does not correspond to rigid rotation of the entire body. It is just the rigid rotation of a neighborhood local neighborhood of the body. Yeah, so it has, of course, the analog of vorticity and circulation in fluid mechanics, and we'll also do that, in fact. Okay, we're going to come to that also. We are not yet talking about the time derivatives. So, anyway, so that's the meaning of this decomposition. You see, it's such a nice physical meaning, no? So, U part, it's the U part which is responsible for generating strain in the body. Change in length, change in angle, change in volume, it's all coming due to U part. And R part is simply the local rotation. Okay. Why we are decomposing? Okay, that's it is just some it gives you some physics, and of course it has importance also later on when we work out stress strain relationship. You will see that U has got uh, U will come there. Okay, when we work out stress strain relationship. So U, it is a U part, it is just to show that it is the U part which actually contains the information of strain of the body, because it is U which is leading to deformation. Okay, so I can also mention that here U part is responsible for generating strain in the body. Okay, and this U has, like I said, it has a some more nice property. Let us try to explore this. So let me write down the formula of stretch again. So you remember that stretch lambda was simply, so if I say lambda at a point x, and for a line element directed along n naught, so that was square root of f transpose f, which is u square, right? U square n naught dot with n naught, right? So why don't we choose and not to be one of the eigenvectors of u? So let us choose and not equal to R1, for example. Okay, and see what do we get. So that means lambda x, and for line element directed along the eigenvector R1, that's equal to square root of u square into R1 dotted with R1. But what will be u square into R1? Anyone? Can you tell me what is u square into R1? R1 is the eigenvector of u square, remember, right? R1 is the eigenvector of u and therefore also of u square. So what will be u square into R1? It will simply give you the corresponding eigenvalue times R1. So that's lambda 1 square into R1. And then you further dot it with R1. But R1 dot R1 is 1. So it is square root of lambda 1 square, which is simply lambda 1. So do you see what is the physical significance of the eigenvalues? So eigenvalues lambda 1, for example, also corresponds to stretching of the line element, which is directed along the eigenvector. So that means if I again draw our body, and here I am at a point x, and if I think of a cuboid, let me make this bigger. So if you think of this cuboid, which is such that the three, so it's a cuboid element, volume element at x, infinitesimal cuboid by the way, such that the three sides are along R1, R2, R3, then what happens to line element along R1? So, so let us try to see that. So if you say dy prime, right? Dy prime is equal to u into dx, right? So that implies, so if you do it for R1, so I would say dr1 prime is then u into, or yeah, dr1, right? But r1 being the eigenvector, u into dr1 is simply lambda 1 into dr1, right? So what you see is that the direction of the line element has not changed. So it was dr1 and finally also it is dr1. I mean, just due to u part, the direction of the line element does not change. If the line element is directed along the eigenvectors of u, then those line elements do not change their direction. They are simply getting stretched by the corresponding eigenvalue. Okay, so that means this part, the cuboid remains oriented in the same way. It's just that its sides are getting stretched. So this is lambda 1 r1, this is lambda 2 r2, and this is lambda 3 R3. Okay, and that's the body. So you see, it has such a nice physical interpretation. So what U part is doing, you can think of a local cuboid whose sides are directed along the eigenvectors. And that cuboid is just getting stretched without changing the orientation. So that's the use of U part. And after U, then you apply rotation part. And this rotation part is simply rotating this stretched cuboid. It is just rotating the stretched cuboid. So I'll write here, rotating the stretched cuboid. Okay. So this U is really very simple. It's like that homogeneous deformation. You remember that we have worked out with three different stretching along three directions. So it is like that. Of course, U here is changing in the body, but locally it is like that. Okay, so that's again a very interesting physical meaning of U. Any question so far? So having seen this physical meaning of U, let us see what was the other decomposition doing, VR. So you have RU equal to VR, which means um, this V is equal to R times U times R transpose, right? So that is the recipe how to get V. So which I wanted to write up here. So number 4, to obtain V, just do R times U times R transpose. Okay, and if you look at the decomposition, if you substitute the decomposition for U here, so this is R summation lambda I small r I tensor product small r I into big R. And now you can bring this R inside, okay, and this becomes summation over I lambda I big R into small r I tensor product big R into small r I. Okay, and this is like if I call this as Li, because that's what the book says, summation over I lambda I Li tensor product Li. So what you see is that V, the eigenvectors of V are little li, okay, and the eigenvalues are same. It's the same lambda I, which is the eigenvalue, and the relationship between little li and little ri is this: little li is big R into small ri. Okay, so rotation tensor is actually relating the two eigenvectors of u and v. So this is for u and this is for v, and it is relating the eigenvectors of the two. Okay, and if I now try to see the physical meaning of this decomposition VR, then we all know that dy is equal to v into r into dx. So it is like v into r dx. So what this tells us is that you have this body, and locally you have infinitesimal line elements dx. you first have to rotate these local line elements through big R. So it's simple rotation, local rotation of those line elements without introducing any change in length or change in angle. And then you apply this big V. And this big V is then doing all the changes in length or angle. So here it is going to have all the changes. All right. And again, because of this decomposition of big V, that means in the intermediate configuration here, you can think of the line elements. For example, this is L1 and that's L2 and this is L3. And these line elements do not change their orientation when you apply V. They just undergo change in length. So this becomes lambda 1 L1. This becomes lambda 2 L2. And the other one becomes lambda 3 L3. Okay. So these line elements do not change their orientation. They only undergo stretching. But other line elements, of course, they have to change their orientation. Okay, so what you see is that these LIs are sitting in the intermediate configuration here, whereas the small RIs, they were sitting in the reference configuration. Okay, I hope it is clear to everyone. So I'm going to stop here and we'll continue tomorrow.
Sir, at the end, the three line elements L1, L2, and L3
Yeah,
becomes lambda 1 times L1, lambda 1 2, like that. So,
yes.
what about the other line elements? What will be the
So they will,
relation?
so they will undergo change. So if you think of any other line element here, let us say L, then this is going to undergo change such that finally it is going to become V times L. And L not being the eigenvector of V, it will undergo change in length as well as change in orientation.
Change in orientation means, sir?
Means the angle, the orientation, the direction of L will also change.
Okay, sir.
Yeah, but for these three, L1, L2, L3, they being the eigenvectors of V, their direction do not change. They are only undergoing change in length. So Sanchita is asking, is there any physical difference between U and V? So discussed, right? So the decomposition is RU and VR. The U part acts directly on the reference configuration, where V is acting on the intermediate configuration. You first have to apply rotation and then V, and for U, you first have to apply U and then R. That's the decomposition. Otherwise, they have the same eigenvalues, right? And their eigenvectors are also related. They have some similarity, but they are not exactly the same.
Sir, but the final like orientation and the elongation will be same, right? Because
Yeah,
you are,
because finally it is RU is equal to VR, no? So final
yes.
line element will be the same. It is just a way to see it, the decomposition. How can we see this decomposition? That's why I have introduced this immediate configuration. Otherwise, of course, you are right that the finally reference line element will change into the same line element.
So in VR decomposition, in the intermediate one, we have L1, L2, and L3.
Yes.
And we said that while we applying R transformation, our configuration, then there is only rotation, there is no change in length.
Correct.
It means in the left one, there is also L1, L2, L3.
Yeah, there are, but they are R inverse L1. So here it will be. So that's a very good question. So here you will have R inverse L1, R inverse L2, and R inverse L3. So that's the line elements in the reference configuration, which due to rotation are changing to L1, L2, L3, and finally due to V changing to lambda 1 L1, lambda 2 L2, and lambda 3 L3. Okay.
It means in the left one, R inverse L1 means length as well as orientation.
No, R inverse, because R is a rotation, no? So rotation does not change length, it only changes the orientation. So R inverse L1 and L1, they both have the same length.
Okay, okay.
Complete rotation, right?
Sir, how did we achieve the diagonalization of U matrix, sir, where we wrote eigenvalues in the diagonal place?
Okay, that's a very good question. Let me see if I can answer that easily. You see, we know that Q into L1, sorry, this is R1, Q into R1, that's equal to lambda 1 R1, right? And likewise, U into R2, that's equal to lambda 2 R2. And finally, U into R3, that's equal to lambda 3 into R3. Okay, so can I write the following? U multiplied by this R1, R2, R3. Isn't this same as UR1, UR2, and UR3? We had seen this while working out the volume change. Remember? So you have two matrices on the left hand side. If you multiply, this is what you will get. But because they are eigenvectors, this is also equal to lambda 1 R1, lambda 2 R2, and lambda 3 R3, right? Now you see what is this? It is just saying that each of the columns are to be what is called scaled by lambda i's. First column is being scaled by lambda 1, second column is being scaled by lambda 2, and third column is being scaled by lambda 3. So you know, whenever you are doing scaling of columns, then it is equivalent to writing as R1, R2, R3 multiplied with, post multiplied with those scaling numbers lambda 1, lambda 2, lambda 3. So you know, when you work out this multiplication, you'll exactly get what is up there. So scaling of columns, so you should remember this, scaling of columns is equivalent to post multiplying with the scaled numbers, with the diagonal matrix of scale numbers, whereas scaling of rows is equivalent to pre-multiplying with the diagonal matrix of scale numbers. Okay, so basically you have to remember, if you are scaling the columns, that means you are post multiplying with the diagonal matrix. If it is scaling of rows, that is equivalent to pre-multiplying. So once you have come here, I can now write that U into the matrix of eigenvector R1, R2, R3 is equal to R1, R2, R3 times lambda 1 0 0 0, lambda 2 0 0, lambda 3 0. And then I just want to bring it on the other side. just apply with the post multiply with the inverse, right? That means u times or u equal to r1 r2 r3 into lambda 1 0 0 0 lambda 2 0 0 0 lambda 3 into inverse, right, into this inverse matrix. But because this r1 r2 r3 they are eigenvectors such that they are perpendicular to each other, so this actually turns out to be an orthonormal matrix. And for orthonormal matrices, the inverse is same as the transpose. Okay, and therefore you can substitute the inverse with transpose.
Sir, time is running out.
Okay, so you can substitute with transpose, and that is what I have written up now, this eigen decomposition. Okay, I hope I could answer you.
Sir, how can we say that U matrix is certainly positive definite? It could be positive semi-definite also, sir.
Okay, that's a very good question. Let me prove that. We know that u square by definition is f transpose f, correct? So let me find out the quadratic product for u square. So u square x dot with x, what is this going to be? This is equal to f transpose f of x dot with x, which is same as fx dot with fx, right? But f being invertible, fx will not be 0 if x is not equal to 0. So here fx is not equal to 0 if x is not equal to 0, because f is invertible, no? So, but here you have the dot product of a vector with itself, so this has to be certainly greater than 0, right? If x is not equal to 0. So that means what you have proved is that u square is positive definite. It's not semi-definite, it is positive definite. And since u square is positive definite, this also implies u is positive definite. Because the eigenvalues are simply square root, no? If the eigenvalues of u square are positive, then for u also it will be positive. Okay, that's the proof.